Hey everyone! I am Miss Hu, your physics teacher. In this video, we will learn about the Doppler effect and redshifting and what it means when observing distant stars and galaxies. We're going to kick things off first with a high IQ comic. So when you look at this, do you understand? Do you understand? Do you understand? Okay, if you don't understand, we'll come back to that at the end of this video. For now, let's look at the Doppler effect. So, what is the Doppler effect? The Doppler effect is not used to hypnotize you. It's actually a concept that is used to explain how come when we hear repetitive sounds, we are able to tell whether the sound is moving towards us, away from us, or moving towards and away from us. So you'll normally hear the Doppler effect when it comes to sound which is very repetitive. So for example, the siren that plays the same frequency over and over again. Ngee-ngaw, 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 ngee-ngaw. So how is it that just through sound alone, we can determine whether the object that's making the sound is stationary or moving? So for example, if these white circles were representing the sound waves that are being emitted from a siren, because of the constant frequency, they have constant wavelength. So from this animation, you should be able to see that the wavelength of all the sound waves, that means the distance between the circles, all are identical. So when the sound source is stationary, we find that the frequency sounds the same, the wavelength is also the same. So there is no changes to the sound frequency. Now remember that sound frequency affects pitch. So if the frequency is constant, the pitch sounds constant to our ears. Now let's compare the pattern of these sound waves of a stationary sound source to a moving sound source. Now obviously these patterns are not going to be the same. So what we'll be observing here is a sound source that's moving from left to right. Now let's say at this position, the sound source emits one sound frequency. So this white circle represents that sound wave being produced. Now as the sound source moves, this sound wave has already been released. So it will continue to move outwards away from its original position. The sound wave is not going to move together with the sound source because it has already been released. So you'll find that the first sound wave will continue to move outwards, in this case forming a larger circle representing the sound wave. The sound source has now moved to the right, and say at this position it emits another sound wave. So you'll find that now there are two circles, but you can see that the distance between the circles is not constant around the circles. As the sound source continues to move, each individual sound wave will also continue to move outwards based on their own respective locations. So you can see how the first circle has continued to move outwards from its original starting position to a larger circle. The second sound wave also has moved outwards to a larger circle than its original first size. And in this position, the sound source has emitted a third sound wave. So if we were to observe the sound source moving, it continues to emit sound waves at every new position, and the original sound waves will continue to move outwards from their own original sources in their own respective locations. And as you can see, the final overall view of all these sound waves look nothing like the first animation that we saw of the stationary sound source. In the stationary sound source, all the sound waves were being emitted at a constant frequency, and because the source was not moving, the wavelength between all those sound waves is equal. However, in this case, because the sound source is now moving, each position will emit a new sound wave, but the original sound waves that have been released will continue to move outwards in their own respective positions. As a result, you'll find that the wavelengths are much larger at the area where the sound source has just left, and the wavelengths are much shorter where the sound source is approaching. Or in other words, the frequency of the sound wave which the sound source is moving from is much lower, while the frequency of the sound waves where the sound source is approaching is much higher. So if we were to be listening to the sound waves of the sound source, so for the listener who is listening to a sound source moving away from them, the pitch is much lower because the frequency is lower. Whereas for the listener to whom the sound source is moving towards, the pitch is higher because the frequency is much greater. So the next time you hear an ambulance, try listening. If the ambulance is approaching you, you'll find that the pitch seems to be much lower. So next time you hear an ambulance, try to listen to the sound to see if you can hear this effect. If the ambulance is approaching you, you'll hear a much higher pitch. Whereas if the ambulance is moving away from you, you'll hear the siren to be a much lower pitch. And if the ambulance is not moving, the pitch remains the same. Now, to explain redshifting, we will use the exact same concept. That means redshifting can be explained using the Doppler effect. So before we go into redshifting, just a quick comparison visually about the Doppler effect. So for a static sound source, the wavelengths of the sound waves do not change. Whereas for a moving sound source, as the sound source moves away from us, the wavelength is increasing. Whereas if the sound source is approaching us, the wavelength is decreasing. So if we were to apply this to light, this will also be the same. If the light source was static, the wavelength of the light would remain the same. Whereas if the light was moving, depending on whether it's moving towards or away from us, we'll see a change in the wavelength. So if the light was moving away from us, the wavelength would be increasing. Whereas if the light was moving towards us, the wavelength would be decreasing. So in terms of sound, we can hear this because different wavelengths lead to different frequencies, which lead to different pitches. For light, how can we observe the difference? So this is where we need to understand how the wavelength of light differs. This can be observed by understanding the visible light spectrum. As you should know by now, the visible light spectrum is the section of the electromagnetic radiation spectrum that is visible to the human eye. This has been covered in the electromagnetic spectrum topic. The visible light spectrum covers the rainbow spectrum, which starts from red, and then orange, yellow, green, blue, indigo, and violet. You must know, of course, that red light has the longest wavelength, and as we go across the visible light spectrum to violet, the wavelength decreases. So what do we mean by red shifting and blue shifting? So what we're looking at here are the absorption spectra. So the absorption spectrum tells us which light has been absorbed. For example, if we were to shine a light onto an object, it will absorb certain light wavelengths only and reflect the rest. So this represents the light that has been emitted from a particular star. So if the star is quite close to us and appear to be not moving relative to us, this would be the absorption spectrum for the particular light. So if, let's say, this particular star was moving towards us, you'll find that the black bands here, which represent the absorption spectrum, have shifted towards the blue end of the spectrum. Well, some might say, it's shifted towards the violet end. It's kind of weird to say violet shifted, so we tend to say blue. So blue shifted. So remember that on the blue end of the spectrum, the wavelength is shorter. That means that if the lines have shifted towards the blue end, the wavelength has decreased. Why we say blue shifted is because the lines are not actually blue in color. The lines have just shifted towards the blue end. So blue shifted. And if you remember what we've just covered about the Doppler effect, a shorter wavelength means that it's moving towards us. So if the light has blue shifted, that means this light is moving towards us. However, if the lines have shifted towards the red end, as you can see over here, the bands have all shifted towards the left end of the spectrum where the red color is. They're not in the red end, it's just that they have shifted towards the red end. So that's why it's called red shifted. So the red end is where the longer wavelengths are, which means that these wavelengths have now increased. And as what we've just learned in the Doppler effect, when the wavelength has increased, it means that the light is moving away from us. So what does it mean when we say light moving towards or away from us? It's about the stars in the galaxy. So if we were to be observing the different absorption spectra of different stars in various galaxies, we'll find that the light spectrum have all redshifted. So looking at this visual here, at the bottom, this is our laboratory reference, which is our control. So this control shows us where the black bands of the absorption spectrum should actually be. When we look at a nearby star, we find that these bands have shifted towards the red end of the spectrum. So now the red end is on the right hand side. Don't remember left or right side, remember the colors. So you can see red end is now on the right side. These black bands have shifted towards the red end, so they've red shifted. For the nearby galaxy, the black bands have shifted even more towards the red. Distant galaxy, even more so, and very distant galaxy, even greater redshift. When you look at all these spectra, you'll find that all the black bands tend to have the same pattern, which means that actually they all have the same kind of element. The only difference is the position of these black bands on the spectrum. That's why we always compare them against the lab reference. So you'll find that the further away the star or the galaxy is from us, the more these spectral lines have redshifted. And what this tells us is that the stars and galaxies are all moving away from us, proving that the universe is continuing its expansion. To understand this more, please watch my video on the Big Bang Theory together with the redshift and cosmic microwave background radiation. So now that you understand redshifting, I hope now you understand this high IQ comic. So when the car is approaching this observer, it's blue shifting, and blue has a shorter wavelength, so that's why we've got a small little compact blue car. But as the car moves away, it's now red shifting, and red has a longer wavelength, so you've got a larger red car. And that is it for this video. So I hope you found this video to be educational and helpful. Do click like and subscribe for more physics lessons from your physics teacher, Ms. Ho. Help me keep making free educational video lessons and lab practicals. Donations are welcomed at my Ko-fi page at ko-fi.com/physicsrocks. For access to notes, quizzes, and syllabus updates, please visit my website at physicsrocks.com. Happy studying!